Generation and recombination of free charge carriers are at the heart of the operation of any semiconductor device, including solar cells. My name is René van Zwaay, and in the next set of videos we will discuss these processes in detail. For this, we will first discuss the relevance of the free charge carrier concentration and its relation with the band diagram, and investigate in more detail the properties of generation and recombination processes in thermal equilibrium and in steady state. Before we get there, however, we first look at an important material property, namely the conductivity. The electrical conductivity of a semiconducting material quantifies the ability of that material to conduct electrical current. The conductivity, often represented by the Greek letter sigma, is given by the following equation. From this equation we see that the conductivity contains two terms. The first term is related to the conduction of free electrons, and the second to that of free holes. Important parameters in this equation are the electron and hole mobilities, indicated by the Greek letter mu, and the concentration of free electrons and holes, given by the letters N and P respectively. The mobility of a free charge carrier represents how well this carrier can move through the material. However, in this video we focus on the free charge carrier concentrations, as it is these charge carriers that will carry the photovoltaic energy. It is therefore important to understand how these concentrations are influenced. For that, we need to consider two different situations, namely thermal and static equilibrium. Now let us first look at the semiconductor in thermal equilibrium. A system, in our case the semiconductor material, is said to be in thermal equilibrium if the temperature of the system is spatially and temporally uniform. This means that the temperature is the same anywhere in the system and is constant over time. This is a rather formal definition, and therefore we will adapt this definition for our needs. We will state that a semiconductor at a given temperature is in thermal equilibrium when no external energy is supplied. For solar cells, this external energy is provided by the photons, but you can also think of heat or injection of charge carriers. In order to calculate the free charge carrier concentration, you have learned to consider the band structure. Here you see the energy band diagram of a semiconductor, with the electronic energy in vertical direction and the position in the semiconductor in horizontal direction. In this diagram, we distinguish the valence band in gray, EV, and the conduction band in yellow, EC, separated by the band gap Eg. According to standard solid-state physics, the density of states, given by the letter G as a function of E, of each band varies with the square root of the energy, as displayed in the second graph. What we see here is how the density of energy states increases when moving away from the band edges. These states are allowed energy states that may be occupied by an electron. The probability that these states are occupied is given by the so-called Fermi-Dirac distribution function. This distribution function is centered around the Fermi level and at a temperature larger than 0 Kelvin has a tail that extends into the bands. The electron concentration as a function of energy in the conduction band can then be calculated by multiplying the density of states function with the Fermi-Dirac function, and we find a drop-shaped distribution. For the whole concentration, the calculation is similar, though we need an adapted distribution function. The important conclusion is that in thermal equilibrium, at a given temperature, the free charge carrier concentration is fully determined by the band structure and the Fermi-Dirac function, and constant in time. However, this does not mean that on microscopic level no changes occur over time. If we were able to follow, for instance, electrons individually, then we see that some electrons may pick up energy from the lattice in so-called electron-phonal interactions and become mobile. We refer to this process as generation and say that the electron has become delocalized, which means that it is not bound anymore to a specific atom in the lattice. This process is displayed in this slide, in which we see that the electron is excited from the valence band into the conduction band. When the electron is excited to the conduction band, charge neutrality dictates that it leaves behind a positively charged hole. The physics of holes has been discussed earlier, and we will consider this as a positively charged particle that can move through the valence band. As such, generation is the process in which free charge carriers are created, with the emphasis on free. Evidently, for reasons of detailed balance, we must have the opposite process, in which electrons may lose energy in interactions with the lattice and fall back to the valence band. This process, in which charge carriers are annihilated, is called recombination. We will now look more closely at generation and recombination in thermal equilibrium. In this slide, both processes are displayed. As we have seen earlier, the concentration of free charge carriers remains constant in time when the semiconductor is in thermal equilibrium. This implies that the generation rate G, that expresses the increase in charge carrier concentration per unit of time, equals the recombination rate R, which is the reduction of the charge carrier concentration per unit of time. In this slide, the subscript N refers to the generation and recombination of electrons, and the subscript 0 to the situation in thermal equilibrium. For holes, the situation is the same, where the subscript P refers to holes. We must realize that generation of electrons and holes always occurs in pairs, and therefore we can state that the generation and recombination rate of electrons is equals to that of holes. Rather than using the generation and recombination rate for electrons and holes separately, we can describe thermal generation and recombination by G0 and R0 respectively. And we find that the generation and recombination rate are equal. Now we move to a situation in which energy is supplied to the system. For instance, by illumination, as is represented here with a photon with energy h nu. In this case, the system is not in thermal equilibrium. We will split up this system in a part that represents the situation in thermal equilibrium, in which N0 and P0 represent the electron and hole concentrations in thermal equilibrium, and add to that the extra electron and hole concentrations that are generated by the illumination. These extra carrier concentrations are usually referred to as excess carrier concentration and denoted by the prefix delta. Now notice that although I show the two parts separately, in reality we cannot distinguish between generated and thermal equilibrium charge carriers. If we consider this situation to be constant in time, the system will be in static equilibrium or steady state. Also, in that situation, electrons and holes will travel through the material and eventually recombine. And the generation rate will be equal to the recombination rate for electrons and for holes. As for thermal equilibrium, we can now also take the generation rate to be equal to the recombination rate, and we can simply describe these by G and R respectively. Now we have defined the generation and recombination rates in thermal and static equilibrium. We now turn our attention to the characteristics of the recombination rate. We do this by looking at the response if we turn off the external generation at time t is 0 and look at the response of the system as it relaxes to thermal equilibrium. In particular, we will be interested in the characteristic time of this relaxation process. In this slide, the generation is shown as a function of time. Before t is 0, the external generation rate is g and independent of time. In addition, we also assume that this generation is spatially uniform. The thermal equilibrium generation rate, G0, is also indicated and will always be present. We cannot switch that off. We are now particularly interested in the response of the carrier concentration to the change in the generation rate, and as an example, we look at the electron concentration in a p-type semiconductor. These electrons are minority carriers in a p-type semiconductor, which is indicated by the subscript p. The electron concentration at thermal equilibrium resulting from the thermal generation rate is indicated by the dashed line in the bottom figure. The external generation rate G before t is 0 results in a higher electron concentration. More precisely, we look at the excess electron concentration, delta NP. We now would like to know how the electron concentration changes as a function of time after the external generation rate G is turned off at t is 0. Therefore, we look for the derivative of the electron concentration with respect to time. The rate of change of the electron concentration is determined by the thermal generation, which is the gain term, and the recombination rate R, the loss term. Let's work this equation out in somewhat more detail. First of all, it is to be expected that the recombination rate varies with the product of the instantaneous electron concentration, Np, and hole concentration, Pp. The prefactor alpha R indicates the likelihood of recombination and is material dependent. We can find a similar relation for the thermal generation rate by realizing that this is equal to the thermal recombination rate and that this is in turn can be written as a product of the thermal equilibrium carrier concentrations Np0 and Pp0. Finally, we apply the mass action law for semiconductors, which states that the square of the intrinsic carrier concentration equals the product of the electron and hole concentration at thermal equilibrium. We now arrive at the differential equation with time-dependent electron and hole concentrations. At this point, we cannot solve this, and therefore we apply the condition of low-level injection. This means that the excess carrier concentration is much larger than the thermal equilibrium minority carrier concentration, in this case the electron concentration indicated by Np0, but much smaller than the thermal equilibrium majority carrier concentration. In this example, the hole concentration in the p-type semiconductor indicated by Pp0. We thus may approximate the total hole concentration by the thermal equilibrium hole concentration, and the differential equation then becomes as shown in this slide. This differential equation can be readily solved, and we find an exponential relationship of the electron concentration as a function of time. I invite you to work this solution out yourself. Here, tau is the lifetime of the carriers. Note that this lifetime is dependent on the thermal equilibrium concentration of majority carriers, the hole concentration in this case. Now we can sketch the electron concentration as a function of time, and then you can see the relevance of the lifetime. This lifetime indicates the time needed for the excess electron concentration to drop to 1 over E of the initial concentration, with E in this case the Euler number. The recombination rate is then equal to the instantaneous excess concentration divided by the lifetime. So to conclude this video, we have seen that at thermal equilibrium the carrier concentrations at a given temperature are constant as a function of time. That in case the generation rate of charge carriers is spatially uniform and that it should be balanced by the recombination rate. We also saw that the recombination rate is proportional to the thermal equilibrium majority carrier concentration of the semiconducting material. I thank you for watching this video and I look forward to seeing you again in the next video.